Until last week, we learned about how to solve second-order linear differential equation using various methods. One is method of reduction order, and the other one was using characteristic polynomial. And also, we learned about how to find a particular solution of non-homogeneous differential equation using method of undetermined coefficient and method of variation of parameters. Now, this is an application of second order ODE, and one application is spring motion. Okay, so there are actually three types of spring motion. You can make it as a 4 if you want, but the first one is free undamped motion. Okay, so free undamped motion means that here. So you're moving, your object hanging on the spring is moving without friction or damping, because of friction. Okay, and there are forces from the spring. Okay, and also the gravitational force. So let me draw the picture that you might see in the lecture, the LMS. So here we have a wall, and here's a spring with spring constant K, and there is a object of mass M. And let's say the units of all the constants are the standard unit, where the unit of mass is kilogram and unit of spring constants is Newton per meter. And let's say this picture is copied to the right hand side of this picture. So we're actually looking at the same one, but let's say if this object is, if there's no object hanging on the spring, then originally this is the length of the spring. And if you start hanging one object of mass m kilogram, then this length is stretched, right? So originally we have length L, for example, okay, and we have a length Y, which is the displacement of the end of the spring because of the hanging object. And you see, well, say that this is delta Y, okay? You see this delta Y times K is equals to mg, okay? And this is a stabilized point. If there is no movement, there is no force applying to this object is not moving. But if you slightly touch this object, then it starts moving with velocity. So there is even further stretching of the spring at some time t. Okay, so let's say this whole thing is y. Okay, and let's say this is small y. So this y measures the entire length of the spring. So large Y, can you see this? Okay, so large Y is the length of the spring at time t. And how do you interpret this small y? So there are both function of t. Large y and small y are both function of t. And small y is the length, so this is the displacement of the object of the mass m from the equilibrium point. So both are unit of meter. If you want, you can make it as a centimeter or millimeter. It doesn't matter. And let's find out all the physical laws applying to this object at time t. So the total force applying to this mass is total force applying to this mass makes the movement of this mass. So this is my double prime. And there are two forces applying to this mass, right? So one is the gravitational force to the downward. And the other is the spring force because of this stretching. So now the amount of the force from the spring depends on the amount of length that is stretched from the original length. So it's going to be k times of, so originally if you make this, if you hang this object, it's stretched by delta y and then stretched further by y at time t. So this is delta y plus y. So this is spring force. And it always applies to the opposite direction, or well, to this direction, or and let's think about the total force. So here is mg, the gravitational force, and minus of k times delta y plus y. Okay. And by the way, we're taking this direction as positive direction and this direction as negative direction. So if the object is moving downward, we take it as a positive. So we took the positive here, and because spring force always applies as the opposite direction to the movement, so we have a negative direction here. And because of this equilibrium point, so at the equilibrium point, the gravitational force and the spring force are the same. So we have k delta y equals to mg, right? So this becomes, cancels out, and minus of ky. Now we have a large Y double prime. So large Y is nothing but L times delta Y plus Y. Now L and delta Y are constant. So if you take the double derivative, these disappears and only Y survives. So we can make this as Y my double prime plus ky equals to 0 as our differential equation. I think that was the problem 1 in chapter homework 1, right? Homework 1 in problem 1 in homework 1. Okay, so so we have this equation. In this slide, I used x for the displacement of the object instead of y. It doesn't matter. This x is the function of t. There's a typo here. So this is not x. This one is dx squared. Okay. And if you make it more simple, then take the m and divide it by m on both sides. You get this equation. Okay. And you see this is a second order differential equation, linear differential equation with constant coefficient. So you can solve, you can find the solution using characteristic polynomial. So the characteristic polynomial is lambda square plus omega square equals to 0, and the roots are plus minus omega and I, the imaginary number. So the solutions are these ones. Okay. So roots are purely imaginary, so you don't have exponential terms. Now we have C1, C2 appears as a arbitrary constant because this is a general solution. You can find a particular solution if you know the initial condition satisfying. So this has to be x again. So I used x and y. I have to be consistent, so this all has to be x. I'm sorry. So you have to find C1, C2 using the initial condition. We'll see the example later. Maybe here, okay. But for now, just think about in general case. So suppose that you found C1 and C2. I want to make this cosine plus sine formula into a one simple sine curve, okay. So then you will use this formula that sine alpha plus beta is same as sine cosine plus cosine sine. So you can rewrite your solution in terms of sine, one sine. But now you have this phase term. So phi appears here. Here. Okay. So if you're simply looking at this solution, then it says the curve is sine function. So sine function is basically measures the x coordinate of the circle. So when t goes to 0 to infinity, that y is sinusoidal. It's like periodic function. So basically, if you have a free spring motion, then the object hanging on the spring is oscillating with the constant amplitude infinitely many times. Okay. So let me explain that formulation here. So this is a standard technique when you have two sine and cosine function added together to make one sine function. So we have C1, is it cosine first? Yes, cosine omega t. So omega here is square root of k over m. Okay. And C2 sine omega t. So now C1 and C2 are real numbers. So let's take C1 square, C2 square, and sum them and then take a square. Because these are positive number, we have real number again. So we have C1 square, C2 square, C1 cosine omega t, and C2, C1 square, C2 square, sine omega t. And let's focus on these terms. Okay. If you draw two-dimensional plane and unit circle, then these are nothing but coordinates of points on this unit circle. So C1 over C1 square, C2 square, C2 over C1 square, C2 square. Because if you take the square of these each coordinates and sum those two squares, then it becomes 1. So you can identify these two numbers as x and y coordinates of one point in a unit circle. And I want the angle between this line connecting the point on the circle and the origin with the positive direction of x-axis as phi. Okay. So then I can re-express this x and y coordinate as cosine phi and sine phi. I'm sorry. So I have to make it opposite. So let's say this is C2 and this is C1. Okay? C2, C1. Okay, doesn't matter. I can interchange this. Okay, because these points are squared sum to 1 when I take a square. So let's take this phi, and then this is cosine, this is sine phi. Okay, so this equation now becomes C1 square, C2 square, and cosine, sine first, right? This is C1 over square root of C1's 2. So sine phi cosine omega t, and this guy is cosine phi and sine omega t. And then using the formula of sine cosine, we get sine omega t plus phi. So if you use C1, C2 instead of C2, C1, you get cosine, cosine, sine, sine. So you get basically cosine expression instead of sine expression. It's totally up to you. And just a matter of choice. It's a matter of taste. So this C1 square, C2 square is the amplitude. The square root of C1 square plus C2 square is the amplitude. And you see, when you find your specific C1, C2, the solution curve will look like a sine curve. So suppose that our sine curves looks like this. But now this says that omega is a frequency. So the period t is 2 pi over omega, right? So let's say t, right? And then the amplitude is square root of C1 square, C2 square, right? And where's the phi here? So let's say this is when sine 0, okay? So this is when sine pi, and this is sine 2 pi. So when I take this omega t plus phi, you have to be careful. This is not the shift of phi. Okay, this is not shifting the sine omega t by phi. If you want to make it as a shifted function, then you have to make it as this way. So this is sine omega t plus phi. Phi over omega this way. So your solution, the solution of y double prime plus omega y equals to 0. Sorry that I just used y again. Is the shifted function from y equals to C1 square, C2 square sine omega t by how much it was shifted by negative of phi over omega. Okay. So this was original function. If you want to shift it, then the x-axis is now shifted to the right side. You're shifting your graph, right? Shifting your graph to the left side, to the left direction by phi over omega. It means that your axis is now moved to the right by phi over omega. So this is our x-axis. I mean y-axis, sorry, y-axis. So and then this is t-axis. So this is going to be phi over omega. Okay. And if you look at this more intuitively, phi, so remark is that phi is determined by C1 and C2, right? In order to define phi, I only use C1 and C2. And where does C1, C2 come from? It comes from the initial condition. So an initial condition of second order differential equations are y0 and y prime 0. The initial position and initial velocity. And let's look at the W here, omega. And omega is determined by what? This is k over m, square root of k over m. So k and m are basic system. The spring system, it determines the spring constant and mass, right? Now, when you model the system with differential equation, we make the system constant and change the initial conditions. So system is not changed. Although you can change your system, but then it becomes totally different differential equations, and you're modeling total different situation. But so usually we don't change the system because the system is what we want to understand, right? So omega is constant. So omega is not changing. Although also this omega determines the period. So this period is purely determined by the system. Okay. What determined by the initial condition, which is variable in terms of in the view of system, is the amplitude and the phase, okay, the shifting. So if you want to understand the system, you try to manipulate your system using different initial condition. You start with the different position and start with different velocity to understand the system. So you can vary your initial conditions, and what changes because of this initial condition is the amplitude and the phase, not the period, okay? And that makes sense because so this is sine curve. This is a periodic curve of the position of the object on the mass. If you hit your object harder than the amplitude, the distance between it, the distance between distance of the object at the minimum, lowest level and highest level, depends on how hard you hit the ball, hit the object in the spring, and that makes sense here. And also this makes sense, although it has a term in omega, it basically determined by the initial condition that you can either hit your object to the upward or downward, and that determines the shape of your graph, solution graph, right? So that makes sense, but that the period t only depends on omega means that you cannot change the period. You cannot change the time that the object goes back and forth to the original position by changing the initial condition. This is the original characteristic of the system. Okay. 질문 있으세요? 이 부분은 중요해요. No questions? Okay, so another system is damped spring motion. So damped means there is a dragging force because of air frictions or because of the liquid. Basically, if your object is moving slowly, there is it's almost no force from the air friction. So because of the spring motion is very slow, considering to the free fall, if you want to put the damping force, you have to put your spring into the liquid or something. Okay. So here's the situation. So damping force is created by resistance between surrounding medium and the moving object. And since the moving object has small velocity comparing to the free fall, we have a damping force proportional to the velocity, okay, not the square of the velocity. So we have a differential equation of this form. Sorry, so we have a differential equation of this form. Okay. So also the damping force always works to the opposite direction to the movement of the object. So how we derive this equation, I think you already done it in the homework, is the same as the previous example, that you have minus kx on the right hand side, and also in here you have extra force, which is minus b times x prime, the velocity. So that's how you get this equation. And you see this equation is also second order differential equation with constant coefficient. So you can solve this by characteristic polynomial. And then I used lambda in here. Although the characteristic equation uses lambda as a variable, I just used lambda, and that's the convention used. And so I changed this differential equation using lambda and omega. Then omega is the same omega in the previous free damping motion, free non-damping motion. And the roots of characteristic polynomials are now minus lambda plus minus lambda squared minus omega squared. And I think you also remember from the homework 1 that showing this is the solution was the problem, one of the problem in homework 1, right? And there are 3 types of solution, right? If you have a positive real number inside of square root, you get 2 real roots of characteristic polynomials. So that's how you get this solution, right? And then let's look at another one. If the inside of the square root is 0, then you get double root. So when you have a double root, you have one root as e to the negative lambda t, right? That was one of the root. And another root can be found by the reduction of order, but you can use the formula of characteristic polynomial. Just simply multiply t, and that's the solution. Okay, and important thing is that we were going to see the graph of these solutions. The critical importance between the first type solution, and second type solution is that they both have a non-oscillation, but as soon as it crosses the second type, what happens is that the solution becomes periodic. So when inside of square root, discriminant of this quadratic equation becomes negative. If lambda square minus omega square is negative, then you get two imaginary roots of characteristic polynomial. And then you immediately have a solution containing the cosine functions and sine functions. And this is not exactly a periodic function because you have exponential term here. So when t goes to infinity, because lambda is positive, you have arbitrarily, your solution gets arbitrarily small because this minus lambda t go to 0. However, in between when this is not 0, and it will never be 0, but you can see at the short time as 다시 들리죠? 잠시만요. 강의실이 너무 더워가지고, 제 방이 너무 더워가지고 카메라가 열받아서 꺼졌어요. 잠깐만요. 이거 좀 엄청 더운가 보다. 또 안 들리면 얘기해 주세요. So where were we? Okay, so 2 is the critical point when it changes from the solution changes from the exponential function to the oscillating functions. So I think at this point it's good to see some examples, but I don't have it in the slide. So let me find an example from the textbook. Okay. And we will see at the end of the lecture how to use the MATLAB to compare the graph of the solutions. So in the spring motion, Let's look at 2.4. So I think that basically, well, let's look at this one. Okay. Let's look at this example. So, except for external force, we have free damp motion. So let me summarize this, the terminology here. So when I say free, it means there's no external force. There's no force applying to the object except for the gravitational force and the damping force and the spring force. So in this example, let's look at the system except for the external force term. Okay. So we have K equals to 2 Newton per meter, and M is 0.2 kilogram, and damping constant B is 1.2 Newton per meter. So this is velocity unit. So Newton times second per meter. Okay. So our system can be modeled by this differential equation: y my double prime plus by prime plus ky equals 0. So I'm using this example, but I'm not taking the external force in count. Okay, so this will be used in the later too. So now it becomes 0.2 y double prime plus 0.2 y prime plus 2 times y equals to 0, right? So let me make it simpler. So we have y double prime plus, by multiplying 5, I get 6y prime plus 10y equals to 0. So I can find this solution using characteristic equation. So lambda square plus 6 lambda plus 10. And roots, there are minus 3 plus minus 9 minus 10. So this is minus 3 plus minus I. There are two imaginary complex roots. So y is c1 times e to the minus 3t cosine t plus c2 times e to the minus 3t sine t. And I have to determine my c1 and c2. So in the question, there's no initial condition mentioned in the problem. So let me see this again. Damping constant, the displacement modeled by. Okay. So let's say in the next slide we have initial condition. This one. Okay. So let's use this one. So x0 is 0.5, x prime 0. Let's take x as y in this case. 0.5 and 0. Okay. So y0 is 0.5 and y prime 0 is 0. So if y0 is 0, then c1 and y prime 0 is also 0, then c1, c2 are 0. That means the object is hanging on a spring without motion and at the equilibrium point. Then if I take off my hands from the object, this is not moving at all. So that's why I get y equals to 0. c1, c2 are 0. But here I had y0 equals 0.5, so I stretched by 0.5 meter, the 50, is it? Okay, 50 centimeter, quite long. So I stretched that object by 50 centimeter from the equivalent point. So if I take my hands off from the object, then it will surge to the floor and surge to the ceiling, right? So it will have a movement. Although at the beginning I don't have a movement. At the beginning, it will move because of the spring force. So plug in this formula. So if I take the 0 here, I get C1 times 1 times 1, so C1. And here I have sine 0, so it becomes 0. So that's 0.5, okay? So C1 is 0.5. So in order to plug in here, I have to take a derivative. So y prime is, take a derivative here, minus 3. I know what C1 is, so I just plug in 0.5 here. So minus 3 times 0.5 times e to the negative 3t cosine t, okay? And then take a derivative of cosine, I get minus 0.5 times e to the negative 3t and sine t, right? And here, same thing, minus 3 c2, I don't know what c2 is, that's what I want to find. And e to the negative 3t sine t, and plus c2 e to the negative 3t cosine t. So when I plug in 0, sine disappears, so that's nothing here. And then I get minus 1.5, this is 1, plus C2, that's equal to 0. So C2 is now 1.5. Okay. So at the slide, I have slightly different C1 and C2 because in the example in the slide, it tries to find a particular solution of non-homogeneous differential equation when there is external force. Here, I don't consider external force. So this is our system. So this is our system. I just want to find the solution of this system with this initial value problem. Okay. So here's our final answer. So y is equals to C1 0.5 e to the negative 3t cosine t plus C2 1.5 e to the negative 3t sine t. So if you want, you can make it into one formula that combining this e to the negative 3t, so 0.5 cosine t plus 1.5 sine t, and you can make it as e to the negative 3t times some amplitude a times sine of t plus phi. You can find a and phi using the formula of sine and cosine. So and then suppose that you already found this a and phi. So I'm not going to find that here. It only takes time. Then the graph will look like basically a sine function, right? Basically a sine function. Can you see this, right? But there is a amplitude which is not constant. A is constant, but there is a e to the negative 3t terms. So if you take this a times e to the negative 3t as amplitude of sine function, this amplitude goes to 0. So you can make an asymptotic line here and imagine that this sine will oscillate between this amplitude. So this yellow line represent y equals to e to the negative 3t times a, and this red line is the curve that we draw here. So this is y and this is t. And you see at the beginning we have to have these initial conditions, so the graph will be flat at 0 because the slope is 0, and it passes through 0.5. So here is 0.5 and it's flat here. It will oscillate infinitely long. It will not flat out. It always oscillate. But if t is quite large, then you will not able to see the oscillation. So in real life, basically it will stop move. So that's the effect of damping. Because there's a damping, it is oscillating at first, but eventually it will stop. But, okay, so here we had, so in the equation, so I erased it, but y double prime plus 6y plus 10, y prime, y equals to 0. So this was b over m, right? And 10 was k over m, right? We had, I'm sorry. So we had a negative term here. So if I take this as omega square and take this as 2 lambda here, okay? So we had negative because lambda, and I'm sorry, so this one was obtained by lambda square minus omega square, right? Omega square. So we had a negative term here, right? Because this lambda was not big enough. So it was 6, so lambda is 3. So if lambda is bigger than square root of 10, then this term will be positive, right? So that means if, where should I put it here? If lambda, or same thing is, since m is not changing, the mass of the system is just constant. Suppose that I'm changing my damper, okay? Suppose I use a stronger damper, then I get stronger, larger b. Okay, so if lambda or b is larger, then what I get is a positive term inside of square root, inside of the formula of the root of characteristic polynomial. We will have the real roots of 4 lambda. I'm so sorry. So this lambda is confusing to you, right? So this lambda is for characteristic polynomial, and this lambda is the standard symbol that we use for spring motion. So just the real roots, okay? So, for example, if we have such system with stronger damper, so that we have 2 real roots, what we get is, let's make an example. Suppose that our b is now 2 instead of 0.2, okay? So m is 0.2 and k is same as 2, okay? So then we have 0.2 y double prime plus 2y prime plus 2y equals to 0. So y double prime plus 10y prime plus 10y. Does it make sense? B is 1.2. Yeah, it makes sense. Yeah. And then Our characteristic polynomial is lambda squared 10 lambda plus 10 equals to 0. So lambda roots are minus 5 plus minus 25 minus 10. So this is minus 5 plus minus square root of 15, right? So your solution will look like y equals to c1 e to the negative 5t, so minus 5 plus square root of 15t plus c2 e to the negative 5 minus square root of 15t. This is our solution. So using the same initial condition that y0 is 0.5 and y prime 0 is 0, you can find C1 and C2. Now, whatever C1 and C2 is, this function is exponentially decreasing when t goes to infinity. So this term goes to 0 faster than this term, right? Because it has a smaller coefficient. The negative is negative of 5 plus 15, square root of 15 is smaller than this one. It both goes to 0, but this goes to 0 faster. So here's one question. Which function determines the shape of function y? Is this one determines the general shape, or this one determines the shape? This one goes to 0 faster than this one. Left or right? So right one is determining the function, right? No. So actually right one, this one determines the solution. It's a nice guess. It has a it's more. This is special than this one because it goes faster than 0. But suppose that your value is really close to 0. Suppose that you're comparing the value between 0.1 and 0.001. So this value dominates this value. If you added these two values, this one dominates. This is unobservable. It's so small that it doesn't changes the entire value 0.1. It changes a little bit, but you cannot see the change. So this does not determine the function. So this determines the function y. Okay. So this is a side note. So when you look at the long formula, and you want to find out the general shape of your function, you have to find out, depend on the nature of the function. If all term goes to 0, you have to find the term that goes the most slowest. So you have to find out the term which goes to 0 slowest, and that determines the shape of the function. So this y is basically looks like this function. Okay, so that was the free damped spring motion. Before I move on to the next one. So let me summarize. So far what we've done is here. So here we have free or forced, okay, undamped and damped. So free means there's no external force. So free undamped is modeled by this differential equation, or let me write it in terms of m and k. So this is my double prime ky equals to 0. And let me emphasize again, this y is not the length of the spring. Okay, y is not the length of the spring, and y is in neither the length, the stretched length of the spring after applying the object mass m. And y is the displacement of the object from the equilibrium point. Let me write it again. So this is very important. The method of finding solution is very simple, but correct interpretation is not easy, and it's very important. So y is the displacement of the object of mass m from the equilibrium point. Okay, and okay, so for free damped y double prime plus ky plus by prime equals to 0. I just switch these two terms. So what's the force damped here? So everything is same, ky plus by prime, but there's an extra force applying to the mass. Okay, so we have ft terms, and the example is such situation here. So let's try to find out the solution of this example. So look at the slide. I will just continue on this board. So we have a same system, 0.2 y double prime, 1.2 y prime, and k is 2, so 2y equals to the external force, which is represented as 5 times cosine 4t. Okay. We want to find the solution to this non-homogeneous differential equation. Okay. How do you find the solution? First, you find a complementary solution from the solution of homogeneous differential equation, right? So you have to find yc from 0.2 y double prime, 1.2 y prime, 2y equals to 0. And we already did that. So this is y equals to c1 e to the negative 3t cosine t, c2 e to the negative 3t sine t, right? Now, we have initial condition that y0 is 0.5 and y prime 0 is 0. I'm not going to apply this initial condition here because this is simply a complementary solution. We're not getting the general solution of the original non-homogeneous differential equation yet. The general solution is the yc plus yp, and yp is obtained from 0.2 y double prime, 1.2 y prime, 2y equals to 5 cosine 4t. This can be solved by method of undetermined coefficients because I can guess my solution will be a cosine function or sine function. So I can I can try my type of function a times cosine 4t plus b times sine 4t and plug into this equation to find out a and b, satisfying this identity equation. And then suppose that we did the calculation already, and then the final answer is just minus 25 102 cosine 4t, and then plus 50 over 51 sine 4t. It's a long computation. It's easy to make mistake. So if I ask this type of question, this type of problem in the quiz or the homework, you have to use the MATLAB. It's better to use the MATLAB or other calculating method, you know. So the general solution now is y equals to c1 e to the negative 3t cosine t plus c2 e to the negative 3t sine t minus 25 102 cosine 4t plus 50 over 51 sine 4t. Okay? And at this point, I have to apply the initial value condition. I have to plug in 0 to find one equation of C1 and C2, and then take a derivative and take the 0. Again, take another equation of C1 and C2 to find unique C1 and C2. So here we have to use the initial value condition. So in the previous example, I didn't have an external force. So that was my final answer, final general solution. But in this case, this is our final general solution. Okay. Now, it's also a long computation to find C1 and C2. So suppose that we already done that. So the answer is look at the slide. We have y as e to the negative 3t times 3851 cosine t minus, the value is not important, 51 sine t. So I'm just want to show you the nature of complementary solution and particular solution. So 50 over 51 sine 4t. Now this part comes from the complementary solution, right? And this part comes from the particular solution. If you're looking at the complementary solution, it will goes to 0 when t is large enough. So as time passes through, this will eventually vanish. The complementary solution does not give any effect on the movement of our object. But in the particular solution, never vanish. This always oscillates. It's a sine function with some amplitude, with some period, okay? So yc goes to 0 as t goes to infinity. So that means y almost becomes yp as t goes to infinity. So that means something because you see, so yc is determined by the system, and yp is determined by the external force. Well, yc also determined by external force a little bit, but yp also determined by the system. There are a little bit of the interaction between the system and the external force, but basically yc is determined by the system. It's determined by this constant -3 and +1 in the cosine, determined by the constant m, k, and b. Okay, that's the system. However, yp is purely obtained by system and the external force. Well, let's say plus the system, okay? and see what actually dominates. YP dominates over YC. So Y is basically behave like YP. So what does it mean? So external force is dominating your movement of the object. Okay. So we had an external force which has frequency 4, right? At the particular solution, we have frequency 4, right? Is it right to say frequency is 4? Anyway, so the period and frequency. Period is same. The period of the particular solution is same as the period of external force. So although there is but however, you see that the system doesn't have the same period. It has a constant coefficient 1 here. So system does not want to follow the same period of the external force, but since there is a damping, this period will almost disappear, and when t goes to large enough, and this movement of the object on the spring will basically follow the same period of the external force. Okay? So reason why it goes to 0 is because there is damping. Because of damping. So here's one question. What if there's no damping, but there is an external force? So the question is, what if the system has no damping, but there is an external force? What happens? So in the quadrant that I draw in the previous blackboard here, we had free motion and forced motion and undamped, damped, right? So we covered the 3 types of motion so far. We didn't mention what happens when there is a force but undamped. So here's the question. What happens if there is no damping but external force exists? So intuitively, no damping means it's basically similar to the free motion, right? So you have a period from the system. So YC is oscillating, right? Because no damping. Always oscillates. And since also there is an external force, YP is also oscillating because of external force. We're assuming that the external force is sine function. Okay. Now we have 2 oscillating functions, right? So the entire solution is YC plus YP. If 2 oscillating functions have same period, then there's no problem. It's basically the sine function, one sine function. What if these 2 functions have different period? What if these what if these functions have different period or frequency? It's called a resonance. So resonance is like you have a one period function inside of another period function. I will show you in the MATLAB session. So in the spring motion, if you make a resonance with experiment, it's very hard because it will eventually, the resonance disappear because YC will eventually always go to 0 because of the damping, right? However, if you experiment with sound wave, then there is almost no friction. There is a friction because of the air resistance, not air resistance. So there's a air in between 2 points where the sound is transmitted from one point to another. So there is a effect of damping because of this air medium. But since this damping is extremely small and it will last for a long period of time, we will see the resonance in the sound wave. Okay. So all the examples are all the examples that I want to show is very contains complicated computation. So we will leave it to the MATLAB session. Okay, so RLC circuit will be covered the next time. Is there any questions? 제가 중간에 매트랩 세션 여러 번 얘기해서 아시겠지만 오늘은 퀴즈를 안 보고요. 근데 가끔 매트랩 한다고 하면 나가는 분이 있어요. 지금도 나갔네. 아, 참. 아니, 몰라도 한번 들어보세요. 유튜브도 끄지 마시고. 매트랩이 중요하다니까요. 질문 있어요? 퀴즈 범위는 스프링 내려면은 너무 더러워져서 스프링은 안 낼게요. 지난주까지만 할게요. 그렇게 해도 꽤 많기 때문에. 자, 이번 시간에는 매트랩 좀 재밌는 걸 할 건데, 이거는 그 웹사이트에서 안 돌아가요. 뭘 할 거냐면 애니메이션을 만들 거거든요. 그러니까 움직이는 걸 다시 들어왔군요. 네, 감사합니다. 움직이는 걸 보여줄 거라 가지고 아마 여러분들이 다운받아서 깔 수도 있잖아요. 그래서 다운받아서 까는 걸 추천드려요. 그래서 뭘 만들 거냐? 일단은 알고 있는 걸 하나 써봅시다. 우리가 아까 했던 매스가 0.2, K가 2, 그 다음에 B가 1.2였죠. 요거를 우리가 한번 풀어봅시다. 자, 이계비병이에요. 그러니까 지금 여기서 spring motion 잘 보이세요? 좀 글자가 작아서 좀 크게 할게요. 설정해서 이게 좀 바뀌었네. 크기를 여기 있구나. 18 정도로 오케이 됐습니다. 그럼 이렇게 하고 지금 점 2 곱하기 y 더블 프라임 플러스 b 곱하기 y 프라임 플러스 b가 1.2죠. k 곱하기 y 그리고 뒤에가 얼마였지? 잠시만요. 좀 찾아볼게요. 5 곱하기 코사인 4t. 그래도 다시 들어와 줬으니까 이거는 제가 한글로 할게요. 말로 설명할게요. 자, 지금 이게 2개 미방이니까 우리가 1개 열린 미방을, 2개 미방을 1개 열린 미방으로 바꿔야 돼요. 이 매틀랩에서 OD45는 무조건 1개 미방을 풀어주는데 1개 미방의 변수가 벡터 형태여도 되거든요. 그래서 그 변수를 벡터형으로 바꾸는데 y1, y2로 이루어진 벡터를 바꿀 때 y1이 y고, 그러니까 우리가 지금 풀고자 하는 이 미방이 y고 y2가 y'이 되도록 바꿀 거예요. 자, 그러면 y''을 했을 때는 y1'이랑 y2'이 이제 항이 되잖아요. y1'은 y''이에요. 그렇죠? y1이 y니까. 얘는 그냥 y''이면 y2예요. 그렇죠? y2고. 그다음에 y2'은 그러니까 지금 등식을 만드는 거예요. y2'은 y''이에요. 그렇죠? y''은 얘들을 넘겨 가지고 0.2 나누기 하면 되죠. 그러면은 5 곱하기 코사인 4t 마이너스 1.2 곱하기 y'인데, 자, y'이랑 y 대신에 y1, y2를 쓰기로 했거든요. 근데 y''이 지금 y2잖아요. y2 빼기 2 곱하기 y1. 그렇죠? 그다음에 요거 전체를 0.2로 나눠야 되죠. 그래야 이제 y''이 되니까. 여기서 나누기 .2. 자, 요렇게 할 거예요. 요게 이제 y''이에요. 자, 그러면은 이거를 우리가 요 마지막 뒤에 있는 요거를 fty라는 함수로 쓸 거예요. 그러니까 지금 y라는 이 벡터 변수에 y1과 y2가 들어가 있는데, 이제 요 y2를 라지 y의 두 번째, y1을 라지 y의 첫 번째, 이렇게 인식을 해가지고 이제 이런 식으로 생각을 할 거예요. y''은 fty다. 이런 식으로. 자, 그러면은 펑션 define 해봅시다. f는 ty 하고 이제 항이 이거예요. 항이. 그러니까 값이, 이 f의 값이 이거잖아요. 그러면은 y2. 자, y2는 제가 그냥 임시로 그냥 붙인 이름이에요. 실제로는 이 벡터 y의 두 번째 항이에요. 그러니까 y의 두 번째. 이렇게 써야 돼요. 그다음에 5 곱하기 코사인 4 곱하기 t 마이너스 1.2 곱하기 y2 마이너스 2 곱하기 y1 하고 나누기 .2. 여기 점 붙여야 될 거 없죠? 오케이. 자, 이러고 나서 ODE ty 하면은 ODE 45 f, 그러니까 요게 우리가 풀어야 될 함수, 그러니까 도함수 값을 가르쳐 주는 함수 f고, 그다음에 이제 범위가 예를 들어서 0에서 한 뭐 10까지 해봅시다. 10은 너무 많은가? 일단 나중에 해보고. 그다음에 이제 초기값이 이 y, 라지 y의 초기값인데, 다시 말하면 y1, y2의 초기값이에요. 그러니까 다시 말하면 y랑 y''의 초기값이에요. y가 처음에 0.5였고 y''이 0이었잖아요. 그러니까 요거 초기값 넣어주고, 이것도 이제 벡터로 넣어주는 거예요. 그러니까 지금 벡터들이 전부 다 이 세미콜론으로 구분되어 있죠. 그 말은 얘는 그 열 벡터라는 거예요. 길쭉한 벡터라는 거예요. 그러니까 세미콜론 한번 들어가면 행바꿈이 되잖아요. 그러니까 이제 행이 여러 개고 열이 하나인 거예요. 자, 이렇게 했다고 치고 이제 일단 우리가 여기까지는 했어요. 이제 그림 그리는 거 플롯 할 때 조금만 기다려 주세요. 왜 안 떠? 뭐 잘못했나? y1 플롯 t, 미안합니다. t, 이거 열을 다 선택해야 되지. 행열. 이렇게. 네. 네, 됐죠? 여기 잘 보시면은 약간 좀 끊겨 있어요. 이게 약간 요 끝이 이렇게 부드럽진 않거든요. 저는 제가 린스페이스를 할 때 그 점 개수, 배열의 개수를 충분히 지정을 안 해서 그래요. 예를 들어서 요 좀 끊겨 있는 것도 제가 이게 린스페이스 시작 끝만 있으면은 기본적으로 이제 배열 개수가 100개로 지정이 되는데 이걸 1000개로 늘린다, 10배로 늘린다 라고 하면은 여기 부분이 이제 더 부드럽게 연결이 돼요. 잘 보시면은 아까 우리가 그렸던 거랑 똑같죠. 근데 지금은 10초까지 본 거예요. 0에서 10초까지. 보니까 앰플리튜드가 쭉 똑같은 것 같아요. 그러면은 좀 더 길게 해보자고요. 100초까지. 10배로 늘려서 해보자고요. 뭐야 이거. 왜 안 줄어들어? 더 길게 해볼게요. 아니 미안합니다. 뭐야. 댐핑. 미안합니다. 이거 지금 external force가 있구나. 미안합니다. 그러니까 있으니까 안 들려드리는 게 맞지. 그래도 좀 이상한데? 잠깐만, 뭐 잘못했나? 잠깐만요. 10까지만 다시 볼게요. 댐핑을 내가 잠깐만 1.2 마이너스 2 하고 0.2 코사인 4t 댐핑 포스를 다 넣었잖아. 다 넣었죠? 0.5 0 다 넣었고 첫 번째 y의 첫 번째 두 번째 잠깐만요. 그냥 어차피 그게 안 나와서 그래요. 그러니까 요게 지금 피리어드가 그러니까 아까 봤던 코사인 4t 있죠? 이제 그 피리어드대로 나온 거예요. 그러니까 yc는 그냥 아마 여기서 벌써 없어졌을 거예요. 그러니까 우리가 지금 피리어드가 계속 연결되는 게 요 텀이 있어서 그래요. 요 텀을 만약에 빼봐요. 네, 아까는 제가 0에서 1000까지 했을 때는 막 이상하게 나왔던 게 이게 구간의 개수가 별 많지 않아서 그렇고 만약에 요걸 빼고 한번 해봅시다. 그러니까 엑스터널 포스가 없다고 가정을 해봐요. 어떻게 되는지 보자고요. 그냥 뚝 떨어지죠. 그러니까 원래 피리어드가 있어야 돼요. 근데 있어야 되는데 거의 안 보이는 거예요. 여기서 이미 이 앰플리튜드가 거의 0이 돼가지고 거의 안 보이는 거예요. 그러니까 엑스터널 포스가 없으면은 그냥 이제 50에서 쭉 다시 이쿠빌리엄으로 갔다가 그냥 가만히 있는 거예요. 거의 가만히 있는 거예요. 조금 움직일 수는 있겠죠. 근데 거의 눈에 안 보인다는 거죠. 자, 근데 이제 예를 들어 가지고 여기에서 댐핑을 한번 빼보자고. 요 부분이 댐핑이잖아요. 요 부분, 요 부분이잖아요. 댐핑이. 요거를 빼면 어떻게 될까? 좀 이상하죠? 좀 늘어났다가 다시 줄어들었다가. 요걸 좀 늘려볼게요. 요거를 한 50까지 늘려볼게요. 좀 보여요? 그러니까 요게 하나가 크게 이제 요렇게 크게 한번 이제 주기가 있고요. 요 사이사이 또 주기가 하나 더 있죠. 그러니까 주기가 두 개인 사인 펑션이 합쳐지면은 이렇게 주기가 뭐라 그러지? 주기 함수가 주기적으로 반복이 되는 모양이 나타나요. 요거를 레조넌스라고 하거든요. 그러니까 우리가 공명이라고 하잖아요. 음량이 이제 서로 공명이 이르면은 막 소리가 증폭되는데 그거랑은 조금 다르게 이제 요거는 이제 우리가 보통 뭔가 소리를 낼 때 항상 이 공명에 의해서 소리가 전달이 되거든요. 그러니까 어떤 뭐 바이올린 악기 소리라든지 모든 소리가 요 큰 주기 있죠. 작은 주기 말고. 작은 주기도 물론 이제 영향이 있겠지만 요 큰 주기의 주기 값에 따라서 소리가 결정이 돼요. 요 앰플리튜드랑. 그래서 보통 소리 그래프에서는 요런 그림이 많이 나오거든요. 왜냐하면 이제 댐핑이 거의 없으니까 공기 중에서 소실되는 이제 음향 크기가 거의 없으니까 해서 이제 요런 오실레이션은 이제 스프링 모션에서 이론적으로는 가능하지만은 실제적으로 관측은 되지는 않을 거고 우리가 이제 우리가 계산할 수 있는 우리가 실험적으로 확인할 수 있는 부분들은 이런 것들, Y2 이런 것들이 살아 있을 때 이제 이런 것 볼 수가 있어요. 자, 근데 이제 요거 말고 아까 하려고 했던 애니메이션을 봅시다. 자, 여기다 10까지만 할게요. 요게 한 개 있었죠. 자, 여기에다가 내가 그래프를 한번 쭉 그려가 보고 싶어요. 그러니까 움직이면서 그리게 하고 싶어요. 이게 잘 전달이 될지 모르겠어요. 왜냐면 스트리밍 하는 거라서 이게 끊기지 않고 잘 전달이 되면 스무스하게 보일 텐데 30프레임으로 제가 전송하는 거라서 잘 보일지 모르겠는데 한번 해볼게요. 지금 여기서 이제 플랫을 한 번에 그리잖아요. 근데 한 번에 그리지 말고 지금 점이 1000개니까 1000개니까 되게 느리겠다. 그쵸? 한 100개로 줄일게요. 그러니까 플랫을 여기서 한 번에 그리지 말고 이거는 이제 잠깐 코멘트를 해놓고 애니메이션으로 보이고 싶으면은 내가 이제 여기다가 100개로 자, 처음부터 I 번째까지만 그리는 거예요. 얘를. 자, 그리고 그릴 때 내가 엑시스를 좀 지정을 할게요. 0에서 10까지. 그 다음에 Y 같은 경우에는 얘가 마이너스 1.5에서 1.5. 그러니까 요 엑시스의 역할은 뭐냐면 내가 그릴 이 그래프 창의 크기를 일정하게 유지시키는 거예요. 그게 일정하게 유지가 안 되면은 그릴 때마다 이 그래프가 최적화된 창 크기로 이제 재설정이 되기 때문에 막 지저분하게 나오거든요. 자, 이렇게 한번 볼게요. 아니, 잠시만. 뭐가 잘못됐어? 미안합니다. 잠깐만. 여기서 요거를 t도 1에서 i번째까지만 그릴게요. 그러니까 여기서 보면은 t가 지금 총 100개의 항으로 이루어진 배열이에요. 근데 이제 그릴 때 1부터 i까지만 그리겠다고 한 거예요. 이 땡땡은 이제 부터란 뜻이에요. 그러니까 앞에 뒤에를 1에서 i번째까지. 그리고 하고 바로 보면은 좀 끊기긴 하는데 보이긴 하죠. 이런 식으로. 그러니까 내가 지금 이 t를 일정하게 0에서 100까지 100개로 쪼개서 움직일 때 이 y가 어떻게 움직이는지를 보는 거예요. 예를 들어서 조금만 더 부드럽게 해봅시다. 1000으로 늘려가지고 꽤 느리겠지만은 보시면은 이제 진행하는 게 보이죠. 잠깐 선 크기를 바꿀게요. 좀 굵게 해서요. 잘 보일 것 같은데. 그러니까 물론 영수철 운동이 이렇게 느리진 않겠지만은 제가 이거는 이제 0에서 10초까지를 1000개로 늘렸기 때문에 아까 그렸던 것보다 10배 느리게 나오는 것 뿐이에요. 근데 어쨌든 시간 간격은 똑같이 내가 맞췄기 때문에 이제 이거를 빨리 감게 하면은 원래 내 영수철 운동, 실제 영수철 운동이 되겠죠. 그러니까 우리가 그래프로 모든 운동이 다 끝났을 때의 그 상태를 한눈에 볼 수도 있지만은 이제 매틀랩으로 우리가 이게 실시간으로 어떻게 될지 시뮬레이션을 해볼 수 있거든요. 근데 기본적으로 방법은 간단해요. 뭐냐면 지금 제가 이거를 할 때 이제 포문을 썼는데 계속 그리는 거예요. 뭘 그리냐? 1에서부터 1까지 그리고 1에서부터 2까지 그리고 1에서부터 3까지 그리고 이거를 그렸다 지웠다 그렸다 지웠다 반복하는 거예요. 그러니까 여러분들 영화 볼 때 이 각각의 프레임들이 그냥 사진이잖아요. 사진을 빠르게 돌리면은 움직이는 것처럼 보이는 것처럼 이것도 지금 결과적으로 이제 1000번 그리는 거예요. 1000번 그렸다 지웠다 하는 거예요. 그거를 이제 우리 눈으로 보는 거예요. 그러니까 이런 식으로 여러분들이 뭔가 그래프를 보이게 할 수도 있거든요. 예를 들어서 조금 더 재밌게 하려면은 요거는 그냥 라인을 그린 거고요. 만약에 포인트를 그릴 수도 있어요. 여기서 봅시다. marker size 하고 20 하고 아까 그렸던 플랫을 이제 갖고 와가지고 여기다 같이 그릴게요. 그러니까 두 그림을 같이 그리는 거기 때문에 홀드 ON을 해주고 여기다가는 홀드 OFF를 해줄게요. 자, 일단은 얘는 끊고요. 자, 여기서 보면은 이 그래프가 얘를 그린 거예요. 처음에 그냥 전체 그래프를 한번 다 그린 거예요. 그런 다음에 빨간색 점으로 이 i번째 위치에 있는 점을 20의 크기로 빨간색으로 점으로 표시하게 한 거예요. 그러니까 이게 이제 점이 따라 움직이는 것처럼 보이지만 사실은 이 그래프 파란 그래프랑 빨간색 점을 찍은 거를 계속 여러 번 지웠다 그렸다 지웠다 그렸다 하는 거예요. 그러니까 이런 식으로 이제 그림을 움직이게 할 수 있거든요. 이러면은 이제 좀 더 움직임이 보이잖아요. 그냥 그래프만 보면은 그래프만 보는 것보다는 그냥 움직이는 게 좀 보이니까 좀 낫잖아요. 자, 그리고 또 뭘 해볼까요? 뭐 이제 거의 다 해봤는데 혹시 궁금한 거 있어요? 이거 그리면서 뭐 더 이런 것도 되는지 궁금한 거, 그런 거 질문 한두 개 받고 오늘 마칠게요. 스피드 높일 수 있죠. 스피드를 높이려면 어떻게 해야 할까요? 얘들을 1000번 다 돌아다니는 게 아니고 10배 빠르게 하고 싶다. 그러면은 10번씩 뛰면 돼요. 자, 이러면은 1부터 100까지, i는 1부터 100까지 가는데 여기서 10i니까 얘들은 10부터 1000까지 가겠죠. 그러면 10배 빨라질 거예요. 근데 이거 자체를, 그림 그리는 속도 자체를 높이고 싶다 그러면은 이게 그냥 자기 컴퓨터 속도에 따라 결정되는 거기 때문에 이 컴퓨터에서는 이렇게 빠르게 이 정도로 되는데 뭐 성능이 더 좋은 컴퓨터에서는 더 빠르게 될 수도 있고요. 성능이 더 낮은 컴퓨터는 더 느리게 될 수도 있어요. 그러니까 맥시멈 속도는 내가 설정을 할 수가 없어요. 근데 이제 뭐 빠르게 하고 싶다면 이런 편법을 하면은 일단은 중지하고 만약에 이렇게 하면은 아까보다 툭툭 끊기냐 10배 빠르게 되고요. 더 느리게 할 수는 있어요. 그러니까 빠른 걸 느리게 하는 방법은 여러 가지가 있는데 이제 여기에서 드라나우를 했잖아요. 드라나우는 역할이 뭐냐면 얘는 이제 이 피겨 창을 깨끗이 하는 거예요. Clear figure. 그래야 그 다음에 그릴 때 안 겹쳐지고 잘 그려지거든요. 여기다가 퍼즈를 하나 넣는 거예요. 0.1초. 그러면은 드라나우를 하고 0.1초 쉬었다가 그 다음에 그려요. 그러니까 성능이 좋으면 이게 거의 순식간에 되기 때문에 0.1초 쉬는 게 거의 의미가 없는데 좀 많이 쉬면은 약간 끊기더라도 천천히 가겠죠.